Hello YouTube, this is my last video in which we're going to finally discuss finding the rate of change of a graph using the derivative, just the definition of the derivative, instead of having to go through kind of the build up to it. We already know what the derivative is. So we're going to go ahead and make a little side note on notation before we proceed with this, but we say given a function f of x, y equals f of x, we say here's our function. We say its derivative function, which is its slope function at any x value, is given as f prime of x. Okay, and we say it is defined this way. It is the limit as h proceeds to nearly nothing, gets up really close to zero, of this f of x plus h minus f of x all over h. And this is what we define as being the slope at any given x value. We often want to find this formula. But in terms of notation, I do want to point this out. Not only do we use f prime of x, but some other common notations of these. We say dy dx, or the derivative of our function y with respect to x is how you would read this. And also this, we say y prime. If I'm going to go ahead and take the time of listing this as f prime of x, we'll also list it as y prime, which would be its derivative. The two you might see in more advanced math texts or just whatever books you're using. I don't know. We don't see this very often where I'm at, but we say this would be the derivative of my function with respect to x. This is the same thing as what I've written here, except for I've just put the f of x kind of next to my derivative here. And this last one is the derivative of y with respect to the variable x. Okay, so we're going to actually, in this example, we're going to find f prime of x. In other words, find the slope at any x, x value for this graph. Okay, and we have a function here of f of x. Then I want to use that function, or that slope function, the derivative, to find the slope of the graph at 4, 3, and 9, 4, for instance. So let's go ahead and talk about this parent function. I think it's good to have a picture. We know that this is a square root function, so it's kind of like a half of a parabola. And we say that I notice here that it's been shifted up 1. So if I go up 1, we'd say it would start here at 0, 1. And we say it has an a value of 1. Observing that here, we say it goes up 1, right 1. And so we'd say this would be roughly kind of a sketch of our square root function here. And we want to find the slope of this graph at, it seems, the point 4, 3 is a point that I'm calling on this graph of 4, 3. And then also at this, we say 9, comma 4. So if we were to go out 5 more to the right here, we'd say 9, comma 4 is on my graph. 9, comma 4. And I want to go ahead and I want to find the slope of the graph at these points. So again, we could use tangent lines to approximate this, but last time I checked, it's not always convenient to use a tangent line on a graph you sketched by hand. So that being said, we can just use the derivative. And so we'll go ahead and get started on this one. We say f prime of x would be equal to this, the limit as h approaches 0 of this difference quotient, where we have f of x plus h minus f of x all over h. Now the thing I want to get used to is this habit of I'm just going to go ahead and fill in f of x here. I mean, with this definition we say it's just f of x. We could go ahead and repeat what the function was here. But in here we're actually going to have to find f of x plus h. And that's something that I tend to do off on the side. If I were to find f of x plus h, this would mean in my original function, wherever I see an x, which was right there, I'm going to go ahead and plug in what we have now. So it'd just be this. And so our function here becomes this, the square root of x plus h, that plus 1, minus the square root of x plus 1, and this is all over h. Okay, so in terms of what we could do with this, well, I'll tell you one thing. This negative here, this difference, we're going to go ahead and rewrite this as a sum. And I notice right off the bat that my 1's here, they cancel out. So I'm just going to re-scribble this limit just to get it cleaned up a little bit here. So we say, all right, here's what we have on top. The square root of x plus h minus the square root of x. And this is all over h. And we'll notice here also, if I wanted to evaluate this limit, going ahead and plugging in a 0 wherever we see an h would yield the square root of x minus the square root of x on top, which is 0, over h being 0 on the bottom, 0. And that would be indeterminate form. So we cannot just go ahead and direct substitute and get indeterminate form. We're actually going to have to work with this. Now, one method we've seen in the past when working with a radical type situation like this is to multiply by the conjugate. And this is what we refer to as rationalizing this expression. So we have the square root of x plus h plus the square root of x. We'll go ahead and take the top and the bottom times the conjugate of the original top expression. Okay, and so what we'll notice is this: we still end up with the limit as h goes to 0. This has not been evaluated yet. But we know the top actually becomes a difference of squares. It has to, because when you multiply conjugate pairs, you always get a difference of squares. And in this case, we say, well, in the first quantity here, we'd have the square root of x plus h. And in the bottom, or on the right side, pardon me, we'd have the square root of x. And squaring both of these out, after rewriting the bottom, I suppose, the bottom is still this, h times the square root of x plus h plus the square root of x. We're going to go ahead and leave this factored. But on the top, to rewrite this again, we have this, the limit, not been evaluated yet, as h approaches 0 of just this. Now I've squared a square root, which instead just leaves this x plus h for the first part, and this will be minus x for the second part. And this is all over h times the square root of x plus h plus the square root of x. And I'll notice this, our x's on the top, they cancel out, and also that I'm left with an h on top and an h in the basement. So I could also say that this h cancels out with this. And so now finally, we have the limit as h approaches 0 of this quantity. We say 1 over the square root of x plus h plus the square root of x. And so this right here, we can go ahead now and direct substitute in a 0 right here. And what you'll notice is this, I get 1 over the square root of x plus the square root of x, which last time I checked is this, 1 over 2 root x. And we're going to give this a name. This is our derivative function, f prime of x, or y prime. And the thing is this, we can now use this to find the slope of this graph when x is 4 and when x is 9. So for instance, I say, well, let's go find f prime of 4. When I plug in an x value of 4 into this formula, I get this, 1 over 2 times the square root of 4, which is really 1 over 2 times 2, which is a fourth. So we get 1/4 is the slope of my graph. And then we say when I find f prime of 9, I'm using 9 on purpose here, it's a pretty number with roots, but we say this would be 1 over 2 times, now I'm plugging in 9 into my slope formula, and I get this, 1 over 2 times 3. Which is 1/6. And I just want to kind of back this up, not with the by hand graph, but if I were to go over to GeoGebra here and say graph this function in. So we had the square root of, we have f of x equals the square root of x, that plus 1. So here's our function. We said we had 2 points. One was at 4, 3, and the other one is at 9, 4. And we want to find the slope of these graphs at these points. Well, we can ask this program to drop in tangent lines for us. So for instance, the slope here, we suspected to be a fourth. We'll notice that this line, this tangent line, does go up 1 over 4, up 1 over 4. So our graph at this point is changing at a rate of 1/4. And then also this, we'll drop in a tangent here at 9, an x value of 9. And we say its slope is this. It goes up 1, 1, 2, 3, 4, 5, 6, right 6, and it continues to do so. So the rate of change of our graph at the point 9, 4 is exactly 1 over 6. So that's how you find the derivative, and that's how you use it to evaluate for slopes at different x values on your graph. Cheers.